In this video lecture, we will go through voids, right? Voids or holes in crystal lattice, right? So these voids are basically, these are empty spaces in crystal lattice. We know that in crystal lattice, we arrange the particles, right? Particles that form a solid, a crystalline solid in 3 dimensions. So when you arrange the particles in 3 dimensions, you see that there are some empty spaces between the particles. Now, there are 2 types of empty spaces that we see in crystal lattice based on the arrangement of particles around these empty spaces. The first type of empty space is called as tetrahedral void, right? And the second is your octahedral void. Tetrahedral void are those voids or empty spaces that are surrounded by 4 particles or 4 spheres, right? If we represent a particle like we did in previous lecture when we studied regarding closed packing, right? Closed packing of particles in 3 dimensions, we represented particles with your spheres. So if a void is surrounded by 4 spheres or particles, we call it a tetrahedral void, right? Because these 4 particles will form a tetrahedron. We'll see it in a while. And the other type of void is your octahedral void, which is surrounded by 6 particles or 6 spheres in crystal lattice, right? So we have first void. We also call these as holes, right? Void is empty space or empty spaces in your crystal lattice, right? Then we have 2 types of voids. First is your tetrahedral void, the second is your octahedral void, right? Tetrahedral void, these are surrounded by 4 particles, right, or spheres. Then we have octahedral spheres, which are octahedral voids, which are surrounded by 6 particles or spheres, right? Simple. Now let's see how it looks in the crystal lattice. These 2 voids look in the crystal lattice. If you look at these 3 black spheres that represent particles, right? These 3 spheres in the first layer, right? And to build the second layer, what we do is we place the spheres in the second layer on the voids in the first layer. So this is a void. If you look at these 3 particles, this is a void. This is a void in the first layer. If we put a sphere onto this void to build this second layer, this is the one that is in red. This red particle or the sphere represents a particle or a sphere in the second layer. So we put this sphere right onto this void which is in the first layer, right? So it will form this kind of a structure. These 3 black spheres in the first layer and this red sphere on the void in the first layer, right? So this is a void, this is empty space, right? If you look at these spheres, these spheres will occupy space in the crystal lattice, these 3 spheres, right? And this sphere as well. But this is empty space between the spheres, right? Which is a void. Since it is surrounded by 4 spheres or particles, we call it a tetrahedral void. Similarly, if you look at this, since I said the other is your octahedral void surrounded by 6 particles, right, or 6 spheres. Now let's see how these 6 spheres, right, are arranged. These 3 spheres, these 3 black spheres represent particles or spheres in the first layer. Now to build a second layer, we will place the particles in the second layer onto the voids in the first layer. So these are, if you are not clear with how to place these, you can watch my previous video on close packing of particles in crystals. So this is the second layer of red spheres which is formed by placing these red spheres onto the voids. This is the void, so we place this sphere on this void. This is the void, we place this sphere on this void. This is the void, we place this third sphere onto this void, right? So these are 3 voids, right? And these are below 3 voids in the below layer, in the first layer. So there is a space, this, which is your empty space between these 6 spheres. This empty space is your void. We call it an octahedral void because this is surrounded by your 6 spheres, right? So this is your octahedral void, right? Now this is your tetrahedral void because this is surrounded by 4 spheres, right? And if you just try to, it will form this kind of a tetrahedron. This here it looks like an inverted tetrahedron, but this is how it will look if you build it, right? These are the center of these spheres, right? And there is a space between the spheres. There is a space, empty space between, which is your tetrahedral void, right? So because this particle is surrounded by a tetrahedron, right? The arrangement of particles around it is tetrahedron, so we call it a tetrahedral void. Similarly, if you look at this arrangement of particle, it will form an octahedron, right? So that is why we call it a octahedral void, because this is surrounded by 6 particles which will form an octahedron. So we call it a octahedral sphere. Octahedral void. So one thing to notice here is these spheres, right? These spheres somewhat like this will form 2 triangles, 2 inverted triangles, like these. It will look like this somewhat. 2 equilateral triangles. Below 3 spheres will form 1 equilateral triangle, and spheres which are in 3 spheres which are in above layer, right, which is in second layer, will form 1 equilateral triangle. And these 2 equilateral triangle have vertices in, or it will look like this, right? Then there is another triangle like this, right? So these 2 triangles with apices in opposite direction. These are 2 apices which are in opposite direction, right? This will, you have an empty space between these 2 equilateral triangles, right, which is a octahedral void. So this is clear. Now let's just little talk about the size of these octahedral and tetrahedral void, and in the next video lecture we will see how to derive the same relations, right? Since in this arrangement we have spheres, right, and between these spheres we have voids, right, which are again circular, right? While taking example of these, while deriving these relations, we'll consider these voids as small spheres and these particles as bigger spheres, right? Particles that form or constitute the packing, right? Packing particle. These are packing particles which occupies space in crystal lattice, and these are empty spaces. The voids are empty spaces in crystal lattice. So these spheres which occupy space will add to packing efficiency. A packing efficiency lecture we have already done before this, right? So these spheres add to packing efficiency, and these voids will not add to packing efficiency because these are empty spaces, right? So to find the relationship between the size of the spheres and the size of the particles, right, we have a derivation for that, but here in this lecture we'll just see that relation, and in the next video lecture we will see how to derive or reach at that relation, right? So here we have the size of the tetrahedral void and the size of the octahedral void, right? So the size of the tetrahedral void is your, let's first say, let R be, since void is represented by a sphere, right? Let R, small r, be the radius of void, and this capital R be the radius of sphere that represents the particle, right? So for tetrahedral voids, right, the radius of tetrahedral void would be equal to 0.215 times the radius of the sphere, or the radius of the particle, right? 0.225, I'm sorry, this is not 215, this is 225, right? So the radius of tetrahedral void is equal to 0.225 times the radius of the sphere, right? If this is the center, then this is the radius r of the sphere, and if this is the circle, this, let's take it in the spherical form. So here this small r will represent the radius of this void, right? And for octahedral void, which is surrounded by 6 spheres, radius of octahedral void is equals to 0.414 times the radius of the sphere or the particle, right? So this is the relation between the radius of tetrahedral void and the radius of the particle, and here the relation between the radius of octahedral void and the radius of the particle, right? And in the next video lecture we will see how to derive these, right? Now let's talk a little about the ionic solids, right? We know that ionic solids consist of cations and anions, right? And we have also studied in previous classes in chemical bonding, or we have studied in periodic table, that size of anions are bigger than the size of cations, right? Because cations have less electrons, so they experience more force, they experience more nuclear force, so they are smaller, right? So the cations are smaller than anions. Anions have more electrons than the neutral atom, so they experience, the outermost electrons or the outermost shell will experience less force, right? So they are bigger than their neutral atoms. So in ionic solids, where anions, right, size of anions are bigger than your cations, right? So since ionic solids are also crystalline solids, right, so they are, the particles, that is these cations and anions, are arranged in 3 dimensions, which form a crystal lattice, right? So the crystal lattice that contains anions and cations, so if we just try to arrange the particles, right, which will form these particle spheres, and which particles among cations and anions will occupy these voids, these empty spaces, right? Since cations are smaller, right, these are smaller, so these will go in these voids, and these are bigger, so these will form packing particles. By packing particles we mean these spheres, right, which occupy space, right, and add to packing efficiency. That is why we call these as packing particles, right? So cations will occupy voids, right, and these anions will form packing particles in case of ionic solids, right? So if you know the size of anions, right, from there you can find the size of cations, since this is smaller, cations are smaller, let's say CR be C small r, be the radius of cations, right, and AR be the radius of anions, right. So if we go by these relations, right, if we know the radius of one of the particles, we can find the radius of the other particles. If we know the radius of anions, we can find the radius of cations, right. I hope all this is clear to you. Now in the next video lecture, we will see how to derive these two relations, right, relation between the radius of or the size of a void and that of your sphere, the packing particle. Thanks.